Chapter 19. We are just mowing them down. Ooh, there's definitely a light at the end of the tunnel. So this chapter is a little bit of an oddball, I'd say. It is a little bit of everything, and you can see from the outline here, it looks like we're going to cover a lot. But the good news is we've seen most of this already. In fact, those are the only two sections that are brand new. So this mini lecture will be a big overview with a heavy emphasis on this part right here, gaining an eye for retrosynthesis. And let's get started. Basically, first things first, this umpalung thing, what is that all about? I don't know what the deal is with scientists. We always have to make something pretty straightforward and turn it into something that's just totally fancy and confusing. Umpalung. What is umpalung? Umpalung is basically saying, you know what? Don't try and make electrophiles react with electrophiles. It's not going to work. No reaction. So if I look at this target molecule right here, I look at that and I think, you know, I could see pulling this apart like this. And, you know, I could see using this as my electrophile. And I'm used to that piece as an electrophile. This is not going to work, though. If I'm going to make this work, I'm definitely going to have to turn this guy into a nucleophile. All that is umpalung. Okay, so electrophile here, because it's a delta positive, right there, plus electrophile here, delta positive. Those two won't go together. But if I umpalung my alkyl halide by throwing in magnesium, I have now changed my electrophile into a delta negative, a nucleophile. And now, electrophile plus nucleophile, that'll work in a heartbeat. As we well know, Grignards love to add to carbonyls, and there's my target. So, umpalung is taking what is normally reactive as an electrophile and converting it to a nucleophile for the purposes of putting pieces together. Another example, if I were to look at this target molecule right here, I would say, yeah, I would want to disconnect that right there because I know I can functionalize at the alpha carbon of my ketone. But when you think of it that way, I'm used to the alpha carbon of my ketone being a nucleophile. And this is a nucleophile. Nucleophile plus nucleophile equals no reaction. So what do? It's not going to work by just trying to react the ketone with the sodium cyanide. So no, I umpalung it. I make the alpha carbon from something that I could consider as a nucleophile, an enolate, and I turn it into an electrophile, the alkyl halide, just like we saw. Oof, that's terrible. Just like we saw on the previous slide. So now this is a delta positive, and I can add my, boom, nucleophile to my electrophile and actually get the reaction to go. So that's all umpalung is. So umpalung is pretty straightforward. Gaining an eye for retrosynthesis, however, as you have already learned, is not. It's just darn difficult to get used to working backwards from your target. So that's the end goal, to work very hard on focusing on your target and forgetting about your starting material. So there's your target right there. Whatever X and Y are, what do you need to focus on? Well, what you're going to focus on is the fact that you have two functional groups right next door to each other. In other words, you have a 1-2 relationship in your target between two functional groups. And I don't really care what those functional groups are. The important thing is that they're right next door to each other, because that is suggesting to you very strongly that somewhere in your synthesis you're probably talking about having either, say, an alkene or an alkyne present, because we know there's lots of functional group transformations, or functional group conversions, that will take an alkene and do electrophilic addition to put functional groups on both of those alkene carbons. So, for example, we know that if I have whatever this alkene is, it's 2, 4, 6, 1, 2, 3, 3 heptene. If I add osmium tetroxide or potassium permanganate to it, I'll get that diol. If I take that heptene and add bromine, I get the 3,4-dibromide. And if I have an alkene that I add bromine in water to, so a bromohydrin, then in that case this would be BROH. Of course, I've got some serious regioselectivity issues here. I could add bromine and methanol and get the bromo ether, and so on and so forth. I could even make the epoxide, and that would allow me to go, for example, to this guy, or maybe to this guy, depending on what Y is. But again, I have some serious regiochemistry issues. It's another thing we need to think about. So, one bell and whistle in terms of retrosynthesis is looking for those relationships. Here's another one, the alcohol disconnection. We've certainly already seen this. This is what we emphasized with the addition of Grignards, that we can plop these electrons back in to generate the carbonyl and kick out Y minus, whatever Y minus is. So when I look at any alcohol at all, I should be thinking, I could probably make that alcohol in one step by adding Y minus. And just to make it really clear again, there are 3 possible alcohol disconnections. Now, what does this look like? There you go. I could add C minus to my ketone. Not C minus, Cn minus. I could add the acetylide. I could add, yes, right? We're adding the enolate in the aldol. So all of these have the same type of disconnection. And all I need to do is examine my target molecule and think, what nucleophile am I going to add to that electrophile? It's going to be Cn minus, the acetylide, the enolate. What else? Well, what else is looking at a target like this and saying, what's the obvious disconnection here? The obvious disconnection here is, boom, this is from way back, and this is because what do we know about ketones? That they have reasonably acidic alpha hydrogens, and that can be deprotonated to make a nucleophilic alpha carbon. So when I see a ketone, I'm going to think I can make that ketone in one step, given that there's some piece on that alpha carbon. I can make it in one step from the enolate precursor. Well, what are we talking about here specifically? Well, for example, we could be talking about brominating the enolate or the enol. That can take place under acidic conditions. We could talk about alkylating the enolate. So what we're talking about here, right, is 1, making the enolate. What should I use? How about a bulky base? Maybe diisopropylamine. And then that gives me the enolate nucleophile, so I need to add a methyl electrophile, delta positive, so I need a leaving group here. Maybe it's iodide, maybe it's bromide, maybe it's tosylate. Totally doesn't matter. How about this guy? Well, hey, pulling it all together here, what we're looking at is, yeah, looking at my target, I can think of it two different ways. I can think of it as the alcohol disconnection, or I can think of it as the enolate disconnection. It's pulling it all together. That is an aldol, right? So an aldol is an enolate plus a carbonyl. So looking at your target and thinking about how can I make this? What's a logical way this thing would be put together? That's what you want to do as you think about synthesis. Here's another way to think about the enolate. Ooh, well, gotta tell you, I'm not really too sure how this makes sense in terms of thinking about the enolate, but it is going to make a lot of sense in terms of that quote-unquote bell and whistle for the aldol, that this is related to the aldol because we're talking about dehydration. It's quite a mess here. Dehydration right here in the E1CB mechanism to get the alpha beta unsaturated carbonyl. So this was, both of these targets are saying think aldol. And finally, what's this one? Well, that one's really pretty clear. I think there we're thinking enolate. So here's our enolate. And we're adding it to what? Well, it looks like we're adding it to this electrophile. Ah. All right, so how do you make this real? Well, you can think of it this way, which is not crazy, but I hope that you'll remember that the 1,5 relationship between the two carbonyls is a Michael reaction. And that, yes, this is an electrophilic carbon. So this says Michael, this says aldol, aldol, alkylation, halogenation. All of which you get keyed in on because you've got functionality on the alpha carbon. So what do you think? Here is a make this kind of compound. Where do we begin? I'm not giving you a starting material. I'm not telling you anything. So I've got two alcohols here. You just need to start working backward from the target. So if I'm going to focus in on my alcohol, I think what I will do is push this guy back in and push this guy out. That gives me this, and I'm just brainstorming now. I could add this organolithium to that, but I've got a big problem. I have an acidic hydrogen, so maybe that wasn't the best disconnection. Okay, let's try again. How about we do instead, let's do this alcohol disconnection. Okay, maybe we're talking about something like this. CH2 minus plus this. Well, now that's a pretty weird looking reagent. There's no way I'm going to be able to make that. But you know, it gives me an idea. Maybe what I need to do is consider adding this enolate to this carbonyl to get the aldol product. Okay, so let's look at that. If I take these two I don't know where I'm gonna go from here, but if I take these two and add them together, I'm gonna get this. So that's good. That's my aldol. I'll worry about this later, how I'm going to make that enolate. And then, back to where I started from. How can I add this when I have an acidic proton there? Well, I think that's chapter 19 chemistry, and it's going to require a protecting group. So, this is as far as I'm going to go on this particular synthesis problem at this time, because all I'm trying to demonstrate is how you start thinking about working backwards from your target. In the meantime, we have to talk about other important things, like this guy who brought home a parrot from the pet shop. The thing that deal with this parrot is that it had a very foul mouth. He started cursing him. He used terrible language. He insulted his wife. So finally, the man had lost it and threw the darn parrot in the freezer just to teach him a lesson. Please don't report the man or me to the ASPCA. So anyhow, after a few minutes, he hears the parrot squawking and screaming. So he thought, well, you probably should get the parrot out of there. The parrot did quiet down, so he opened the freezer door. The parrot walked out and looked at him and said, I apologize for offending you, and I humbly ask for your forgiveness. The man said, well, I thank you. I forgive you. And the parrot then said, if you don't mind me asking, what did the chicken do? Yeah, pretty bad. Okay, well, so we're diving into 19 with both feet forward. We're going to focus a lot on synthesis, a little bit of new chemistry to learn. Hang in there, get your water wings, and we will be fine.